All right, it's circle time, everybody's favorite time. So we are out of the woods of triangles, or so you think, and we are headed on the world of circles, the round world of circles. All right, so this is how we call something a circle. We're going to call this circle C because it is labeled by its center point here, and I called the center C because center starts with C. You can call it whatever you want, but I stuck with C. So circle C with a little dot right here. Don't make fun of my circles, please. So, things you know about circles. Well, you probably know about these things called radii, a radius, right? And a radius is a segment that goes from the center of the circle to the outside, the circumference of the circle. And we call those radii. You can draw as many as you want, right, in any direction. And the cool thing about radii is that they're always going to be the same length. So, for instance, if I were to draw two radii like this, if this was an actual circle and not just something I freehand drew, this length right here between A and C would be the same as the length between B and C. So that's kind of neat. These lengths right here are congruent. Another thing you probably know about circles is that we can do the circumference. I mentioned that earlier, and the circumference is just a fancy word for the perimeter. It's the length around the circle. So if you can imagine taking a piece of string from A and going all the way around back to A, and then taking that piece of string and stretching it out so you can measure it on a ruler, that would be the circumference of the circle. So when we're talking about central angles, what we're talking about are angles that are formed by the center and two radii. So we have a center and two radii. So the angle that's being formed by them, this angle right here, is a central angle. So angle ACB is a central angle. And what's cool about the central angle is that the angle here, we could imagine measuring closer, right? It would still be the same angle. So for instance, if this angle right here was 60, if I measured it here, it'd still be 60, right? It's still measuring the same angle. If I measured it out here, it would still be 60. And if I measured it out here, it would still be 60. And you can imagine measuring it all the way out here. Well, that means this arc, this piece of the circumference, this arc right here, which I'll highlight in yellow, is also going to be 60, right? Because we can keep measuring this angle and even measure it out here where this arc hits. And so this arc should also be 60. So we have an arc right here that is 60 degrees. So if this was 60, then the arc that it subtends, the arc it opens up into, is going to be 60 as well. So there's that relationship there. Whatever the arc is here is what is here. And this makes sense because you know a full circle is 360 degrees. And if you notice, we've created two central angles here, a minor central angle, the 60-degree one, and also this one that I'll be highlighting in blue. So this angle right here, right? So we have this angle right here that is going to be 360 minus the 60 that's here. Well, that's going to be a 300-degree angle, right? And altogether, they'll make 360. And you can imagine that angle, right, that 360 angle right here, going out further and further and further until we hit the circumference of the circle, meaning that the circumference, the whole thing will be 360. And we've already taken 60 away from it, so what's left over, this portion out here, which I will outline in this light blue, this arc right here would be 300 degrees. So that's an easy enough relationship to remember. The central angle opens up into an arc of the same measure. This is always true. So let's talk about these arcs. How would I write them? How do I talk about them? Etc., etc. Well, arc AB would be written like this. Little arc symbol. It's kind of like a curve over the top, kind of like an arc itself. And the measure of arc AB in this case would be, well, 60 degrees, because the central angle that subtends it is 60 degrees. And if I were to talk about this arc right here, well, we'd also call it AB, right? So what's the deal? How can we differentiate between the two of them? Well, there's one way. We could drop another point and call it D, and then we have arc ADB, and there's only one way to connect those in order, right? The blue arc right there, and that would be 300 degrees. The other way to do it is to specify the difference between these arcs, and I alluded to it earlier. This is a minor arc because it is less than 180, so this is a minor arc. And this would be the major arc because it is more than 180. So we could say minor arc AB and major arc AB without having to drop point D to differentiate differentiate, right? The major arc is going to be this one, and the minor will be that. So that's just some new nomenclature. All right, so this is the relationship between central angles and their arcs. Now let's talk about what makes an inscribed angle a much more interesting relationship and probably a little less obvious. So let's draw another circle. You'll get to see me do it in real time. All right, so here it is. Beautiful, excellent. Everybody loves my circles. And here's the center point. So says I. And what's interesting about inscribed angles is that they're not central angles, so they're not going to be formed by radii from a center point. In fact, they're going to be formed by 3 points on the circumference. So if I choose 3 random points, let's choose this point right here, this one here, and this one right here, they will form an angle, which is not a central angle because it's not coming out of the center, that we call an inscribed angle. And the reason for this is because it is inside the triangle. Scribed, it is written inside the triangle. So an inscribed angle. And notice it does not go through the center. Otherwise, it would be a central angle if that was the vertex, right? So let's call this A, or how about you? Let's use XYZ. How about that? XYZ. We've already used C for our center. So XYZ. So we've got inscribed angle XYZ. I would write it like this, angle XYZ. And that's going to be an inscribed angle. And you'll notice that this angle opens up into an arc. So let's highlight that. And the question is, what is the relationship between this inscribed angle and the arc it subtends? Now, for central angles, it's pretty easy, right? We've got, if this is 60, this is 60. If that's 300, that's 300, blah, blah, blah. It divides up a little circle on the inside the same way it would divide up a circle, a wider circle on the outside. But this is a different beast entirely. So it turns out the relationship here is that this angle's measure, the measure of angle XYZ, is going to be equal to half the arc that it subtends. So whatever this value is, we're going to divide that by 2, and that's going to get us our angle here. So I'm going to write that half of arc XZ. So I'll write that, arc XZ. So that's the relationship. So plugging in some numbers. If I knew that the arc over here was, let's say, it looks more than 180 to me. Let's make it 200 degrees. If that was 200 degrees. Well, if this whole arc is 200, then the angle is half of that arc. Well, the arc is 200, and half of 200 is 100. So that would mean this angle here is 100 degrees. So that's 100 degrees right there. So notice the relationship is kind of a 2-to-1 relationship. If they give you the angle, the inscribed angle, then you know the arc is double that. And if you're given the arc, well, then you know the angle is half. It goes both ways, right? So that's the relationship between inscribed angles and their arcs. What's also cool about inscribed angles is that if I was to draw another inscribed angle on here, and I'll do that in blue, and I use the same points except for the vertex. So if I don't know, let's use this guy right here as the vertex. We'll call it W. So if I made an inscribed angle, XW, Z, you'll notice that this inscribed angle opens up to the same arc. So if it opens up to the same arc, then it's going to be the same value, right? Because it opens up to this guy. We divide this by 2, and this is going to give us our angle here. So this is also going to be a 100-degree angle. So that's pretty dope. So if inscribed angles open up to the same arc, they're going to be the same angle. So what about this inscribed angle? And this central angle. Here's some interesting ones. So I'm going to put my center here. Here's center C. And I'm going to do 2 radii that are collinear. So the points A, C, and B, here's A, here's C, here's B, are collinear, which means that these radii are a single line. These 2 lines make up a single line, which means this is a diameter. Right, it's twice the radius. You probably remember this from your basic geometry days back in elementary school or middle school. And what's cool about the diameter is that it cuts the circle in half, right? Perfectly in half. So if it cuts the circle in half, and this is a central angle, and we know that this angle is 180 degrees. I'm sorry, 180 degrees because it is a linear pair, right, or a straight line, right? We've got a straight line, so a straight angle is 180 degrees. That means when it opens up into this arc right here, the arc is also going to be 180. Again, this is a central angle, so the relationship is 1-to-1. Whatever the central angle is gives us the arc. Now, if I were to draw an inscribed angle, like, I don't know, maybe this one right here, that opened up into the same part as this central angle. Let's call this D or ADB, angle ADB. It's an inscribed angle. So we know the inscribed angle, if it opens up to the arc, the angle here is half. So that angle is going to be 90. So that's kind of cool. And it turns out any time that I have an inscribed angle that opens up to the diameter, it's going to be a 90 degrees. So whenever we have a diameter and we have an inscribed angle connecting to it, it's always going to be a 90 degree. So if I were to draw, for instance, another inscribed angle, like choosing this point right here, well, because it opens up to the same arc, it's going to be the same measure, so it's also going to be 90. So we have all these right triangles that we can make. I'll draw one more just to make it look interesting. Let's pick this point right here. And if it opens up to the diameter, it'll be 90. So we have all these different right triangles we can make. And this makes sense, because if this is 180, then the inscribed angle that subtends that has to be half that, which is 90. So those are always going to be 90. Some interesting properties. So the big thing that you need to look for doing problems like this are, one, that the central angles always open up to the same measure as their arc, and the inscribed angles open up to an arc that is double their size. So if the inscribed angle is 100, the arc they subtend is 200. And if two inscribed angles open up to the same arc, then they're going to have the same value. It's really useful to be looking for these inscribed angles. The other thing is that when you have an inscribed angle that hits the diameter, right, the circle is cut in half, so half of this arc will be 90. Things to look for. All right, so that's central angles and inscribed angles. Let's do an example of a problem involving them. So how about this? We've got a circle, and we've got a center. Let's call it point C. And from that center, I've got some lines. I won't color code them, so maybe we can get used to seeing them without color. But you're probably already guessing that those lines are radii, and you would be correct. So let's draw this. We've got this funky looking triangle that has triangles within it, and my drawing skills are peak. All right. So we've got point C here that you can't really see because it's covered up by that line. All right, so what we want to do for this is we want to solve for these arcs here. So if I know that this angle right here is, I don't know, 100 degrees, and this angle right here is 100 degrees, and this angle right here, well, it's going to be 360 all around, so maybe that's 160. I can tell that this arc right here is going to be 100 as well, because this is a central angle. We've got two radii here opening up to an arc. So this arc will be 100. And as well as this arc over here will also be 100, despite the drawing looking like it will be bigger. And that means that this arc here is 160. And this makes sense because if we take all the arcs, they should add up to 360. And they do. Additionally, you might notice some inscribed angles here. This angle, not this angle right here. This angle right here, right, is an inscribed angle. So if this is 160, it opens up into 160. Remember, an inscribed angle is going to be half that. So the measure here, let's highlight that in blue, of this angle all the way across is going to be half that, which is 80 degrees. Well, we have another inscribed angle here, opening up into the right arc. So that means this angle over here is going to be half that, which, of course, is 50 degrees. Let me pull another color out of here. Let's use red. So that angle right there is going to be 50. As will this inscribed angle here. So inscribed angles open up into an arc that's double what they are. And central angles open up into an arc that's the same. Let's do one more example problem. Here's one with some inscribed angles. There's a circle. And I'm going to tell you that K is the center. And this is G. This is J. This is I. And this is H. All right, so when I connect all this stuff, I've got this, and this. All right, I've got some funky looking triangles here. There we go. Bless me. All right, so we're here. We've got some triangles. And I'm going to give you that this angle measure right here is 20 degrees. Additionally, I'm going to tell you that this arc is 90 degrees. And we're going to solve for all the parts given this information. So the arc is 90, the angle GJH is 20, and you'll notice right away that, or at least I hope you do, that this angle GJH is one of our inscribed angles. So if this is 20, the arc that it opens up into is going to be double. So this arc right here is going to be 40 degrees. Again, this opens up into this arc, so it's going to be double whatever the angle is. All right, so this is 40, and you'll notice that we have another inscribed angle that opens up into this. Well, if this is 40, and this opens up into it, then these two inscribed angles, GJH and GIH, are going to be congruent. So this is also going to be 20 degrees. Alrighty. So you'll notice some more inscribed angles, I hope. Here's an arc 90, and we have an arc that opens, or an angle that opens up to it, an inscribed angle. So it'll be half of whatever 90 is, which of course is 45 degrees. You'll notice that we have another inscribed angle right here that opens up into the same arc, so it'll be congruent. That's another 45. So we've solved for these angles here, and now we can get this angle right here. So notice we have a triangle. This is 45 and 20, and the internal angles of a triangle always sum to 180. So we've got 65 between these two. So left over, we're going to have 115. Because 115 plus 65 is 180. And you'll notice by vertical angles, this must be 115 as well. This right here is a linear pair, so they have to sum to 180. Also, these are remote interior angles to this angle right here. So this angle, let's not use red, let's use a different color. How about, run out of colors here, how about light green, this minty green? Well, this is a linear pair, so these have to add to 180, so this is going to be 65. And then again, by vertical angles, I can call this 65. So that's kind of cool. So we've got all the angles here. The only two angles we don't have are these two. And the reason we can't find them is because this inscribed angle is opening up to this arc. And we don't know anything about this arc. We're not sure how these angles are situated, these arcs right here. If we knew about these arcs, we could fill these out. But we don't have the resources to do so. So those are inscribed angles, complete with, actually, you know what? Yes, we can. I forgot. This problem has an interesting property. I changed it at the last second. Hopefully you're sticking around. This dot right here is the center, right? So K is the center. And that means this is the diameter, right? Because we have two radii that are coming from it. And they are collinear, G, K, and I. So that means this whole arc right here is going to be 180 degrees. Well, if this arc's 90, this arc must be 90 as well, because they must sum to 180 degrees. So I'm running out of colors, but I will try to do like a light pink. Let's try that. And this is going to be a 90-degree arc. Well, if the arc is 90 degrees, this angle right here is actually, we're going to be able to figure out, it's going to be 45 degrees. Half of the arc it subtends, right? These are inscribed angles. Well, and if that's 45 and that's 65, we get 110. And so the leftover angle right here, which I'll do in purple, is going to be 180 minus 110, which is 70 degrees. So now we've got all these angles, and all of these angles. The only thing we're missing is this arc right here. Well, you'll notice that this inscribed angle is 70, and it should open up into this arc. So if that arc, or if that angle is 70, that inscribed angle, then the arc is going to be double, which of course is 140. And let's check our work. We've got a 90-degree arc plus a 40-degree arc, that's 130, plus another 90-degree arc, that's 240, and 240 plus 160 is in fact, wait, did I goof that? 240 plus 160? I think I might have done that. Yes, it's not 240 here. We've got 90 plus 90 is 180, plus 40 is 220, and then we have 220 plus 160, which is, of course, oh, it's not 160. I keep seeing that. Plus 140 is going to get us 360. Good thing we check our work, right? We've got the 140-degree arc. We've got the 90-degree arc. We've got the other 90-degree arc, 90. A 40-degree arc, that blue one. And that'll give us our four arcs. And if they sum to 360 like they should, we probably did our work right. Again, good thing I'm checking. All right, so we have 90 and 90 adding together. That's going to make 180. And we've got 140 over here and 40. And again, the easiest way to add these, I think, is to make these 180. So we have 180 plus 180 from these two adding together. And, of course, this is going to make 360. So we should have done our work right. All right, so those are inscribed angles and central angles. Again, watch out for them. Really look for those inscribed angles. It's sometimes hard to see all of the different inscribed angles that are here and what arcs they open to, and that some inscribed angles open up to the into the same arc. These are some key observations you need to get used to. So be on the lookout for those. Inscribed and central angles.